Hello, and welcome to the fifth and final section on our unit on oscillatory motion and waves. In this unit, we are going to be looking at interference. So what is wave interference? The easiest thing to do is to show you. So I'm going to pull up this simulation where instead of waves, what we're dealing with is pulses. So we have a rectangular pulse and a circular pulse, and you can see when they overlap, they add together. Now, right now, I would say that they are constructively interfering because where we had the two separate things, they combine to make something bigger. So that is constructive interference. On the other hand, I could make destructive interference by flipping one of them over so that when they add together, that white line gives me something smaller. What I will say also, I'm going to go back to the first one here and make it so I can control it here. If you look, we have a blue wave, we have a red wave, and we have the white one that is the sum of the two. So if I look right now, blue is 0 through here, right? Do I have that right? Blue? Yes. Blue is 0 through here, then picks up. Red is 0 over here and then picks up. And right now it's just following the shapes that they are individually. It's when these things start overlapping that I get more fun. So if I come along from this side, I got everything 0. And then the red elliptical wave or pulse turns on, so it starts moving upward until the rectangle turns on as well, and then I jump up again because I'm adding the height of the red one to the height of the blue one and getting something twice as high because they're equal. And then that trails off as the ellipse trails off, and then I follow the rectangle out. And I can do this with any of these. So let's go look at, say, triangle, triangle. What does it look like separate? I have two triangles, the red and the blue. And when I put them together, maybe, all of a sudden I start getting this spike because they're adding. Right? So at this location, the red is a little bit on, the blue is off. And then the blue really turns on while the red is still basically off. And amazingly enough, when you add these two together, it gives you a flat line across, and then it repeats, but in the opposite order on the other side. If I go to triangle 1 and triangle 2, separate them, you can see one is up and one is down. So when they start adding together, I get something smaller. And that is what interference is. It's the addition of two waves or two things together. Interference or superposition, the addition of these two waves, can occur in both space, which would be a standing wave. Now we're going to cover standing waves in the next unit or next chapter, as it says here. It's part of chapter 17. It can also occur in time, which is a beat frequency. And we're going to look at what a beat frequency is on the next slide. So a beat frequency occurs when you have two waves with slightly different frequencies superimposed on each other or interfering with each other. And I have a wonderful demo for this as well. So here I have a blue wave at 250 hertz, a red wave at 257 hertz, and if I overlay them, you can see that over here they're moving out of in sync with each other, and then they're in sync over here and they move out the other way on this side. And if I turn on the sound for this, you can hear it oscillate. Wah, 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 wah. That oscillation is the beat frequency. If I make these two waves closer and closer together and play it again, the beat frequency now is much smaller. On the other hand, if I move them further out, very different. So bringing it back in a little bit again. Let's see, 252 will work. Okay, a useful application of beat frequency is for orchestras. When you go to see an orchestra, they always play a note together at the beginning to show how in tune they are to each other. What they're listening for are beat frequencies, and they're trying to adjust that beat frequency so that it is as small as possible. Beat frequencies are very simple to calculate. So the beat frequency equals the absolute value of the difference between the two frequencies that you have. Okay. So as an example, if my beat frequency is 5 hertz and F1, one of my two waves causing the beat frequency, let's say, is at 250 hertz, then F2 could equal either 245 hertz or it could equal 255 hertz. Because when I take 250 minus 245, I get 5 when I absolute value it. And if I take 250 minus 255, I also get 5 when I absolute value. I would love to tell you that this is the simplest formula in physics, but there's actually one easier. This concludes this part and this unit. In the next unit, we're going to continue studying waves. We'll do standing waves, and we're also going to focus in particularly on sound.